This is problems 93 and 94 from chapter 12. This diagram is for both problems. In 93 and in 94, the golf ball is struck with an initial speed of 80 feet per second at the angle shown in the diagram. In problem 93, we want to find the distance, d, to where the golf ball will land. That's the distance between point A and point B in the diagram. And for problem 94, we want to find the speed at which it strikes the ground at point B. So that would be the speed, which is the magnitude of the velocity at point B, and the time of flight, delta t. We have two equations to use. These are modified versions of equations 12.5 and 12.4. And we're going to draw a vector diagram for this equation here in order to find the distance and delta t. One thing to be aware of here, if you look in the diagram, the angle for the slope is 10 degrees, and then the 45 degrees that they give you is between the surface of the slope and the angle that the golf ball is hit at. So if you're measuring the angle for the initial velocity from the horizontal, that would be 45 degrees plus 10 degrees. That's how I usually measure the angle. So I would say the angle for the velocity here, let's just draw it up here, is at 55 degrees from the horizontal. Okay, so we're going to start off by drawing a vector diagram for this situation. So delta S goes from where the object started to where it landed, so that vector should be at an angle of 10 degrees, and it goes from point A to point B. So this is our vector delta S. You can add the 10 degrees there just in case we need it later. The acceleration vector should be pointing straight down, so somewhere on that line there. And the initial velocity is at an angle of 55 degrees, so that's something like that. This angle shown going from the horizontal to the velocity vector is 55 degrees. And this is the velocity times delta t, and then we have 1/2 times the acceleration times delta t squared pointing straight down, and I can make two right triangles by drawing the horizontal line and this vertical segment here. If you draw the vector diagram right on the initial diagram that we had, that would be something like this. Okay, so my angle is not quite the same as what I had there, but let's instead just take the trajectory of the golf ball and add it to what we have here. So initially, it should be more like that. The golf ball is going at an angle of 55 degrees, and then at any time after that, this vector is not going where the golf ball is. So this vector is always going to be higher than the path of the golf ball after it's initially hit. So these two vectors are not telling you where the golf ball is at any point in time along the way. It's just showing you where the golf ball lands. If you wanted to find where the golf ball was halfway through the time of flight, you could draw a new vector diagram. Halfway through, delta t would be half of what it is here, which would make this vector half as long, and then delta t here would be half what it is if you're looking where the ball is halfway through the time of flight, which, since it's squared, would be 1/4. So you'd have a smaller vector pointing down like this, which would show you where the golf ball is halfway along the way. Okay, so this vector diagram that we drew is really only useful for the final point that we're looking at. Okay, so I think I have everything on that I need for my diagram there. So I'm going to compare this segment here for the two triangles I have. So one of those is with delta S as the hypotenuse and this angle being 10 degrees. So this distance from here to here is delta S times cosine of 10 degrees, but then we have another triangle like this with an angle of 55 degrees and a hypotenuse of VA delta t. So this is also equal to VA times delta t times cosine of 55 degrees. So that's going to be my first equation. I'm going to write that over here. Delta S times cosine of 10 degrees is equal to VA, which is 80, and, oh, actually delta S is supposed to be little d. I think I'll just put that over here and keep it as delta S since I already wrote it that way. And so VA is 80 feet per second times delta t times cosine of 55 degrees. I can get another equation by looking at the vertical side. So from here to here is delta S times sine of 10 degrees. And if I take this and add to it this piece here, which is 1/2 the acceleration times delta t squared, that gives me the whole length from here to here. I'm going to draw it over here because I'm running out of room. But that would be the hypotenuse of VA times delta t times sine of 55 degrees. So that's the whole distance from here to here. And that, putting in an 80 for VA, is equal to this piece here, which is delta S times sine of 10 degrees plus 1/2 of the acceleration, where the acceleration is 32.2 feet per second squared, and we have already seen 1/2 of 32.2 is 16.1, so let's just call that 1/2 A 16.1, and that is times delta t squared. Well, then, let's see what we have. I have delta t, which I'm going to want to find, and I have delta S. So I have two unknowns. And I said in a previous problem, it's usually a good idea to keep the delta t and get rid of any other unknowns. So in order to do that, I'm going to solve equation 1 for delta S, and then I can substitute that into equation 2. So to solve for delta S, I just need to divide by cosine of 10 degrees. So I have 80 times delta t times cosine of 55 degrees divided by cosine of 10 degrees. And I'm going to take this and I'm going to put it into what I have there. So now I have 80 times delta t times sine of 55 degrees is equal to delta S, but delta S is 80 times delta t times cosine of 55 degrees divided by cosine of 10 degrees plus 16.1 times delta t squared. This equation is kind of nice because there is a delta t in each term and there's a delta t squared here, so you can cancel out one of those delta t's, which is what you would get by dividing everything by delta t. And now we just have one delta t left. So because we didn't have any terms without a delta t, we didn't end up having to use the quadratic equation, the quadratic formula, which is very nice. And so now we can just solve for delta t. So I can subtract this from both sides and divide by 16.1, and I have delta t is equal to 80 times sine of 55 degrees, bringing this over to the other side would be minus 80 times cosine of 55 degrees divided by cosine of 10 degrees, and then to get delta t by itself, we have to divide by 16.1. And now I see that I forgot something when I did this. So I was supposed to put this in for delta S, but it was delta S times sine of 10 degrees. So there should be a sine of 10 degrees here. And then when I bring this over to the other side, I'd still have this sine of 10 degrees. And you could take this sine of 10 degrees divided by cosine of 10 degrees, and you could call that tangent of 10 degrees. I'm not going to rewrite it that way because at this point you can just go ahead and plug it into your calculator, but to make it a little easier, you could just plug that in as tangent of 10 degrees. And you get to solve for delta t on your own, and you should get 3.568 seconds. 3.568 seconds. If this was the final answer, you could go ahead and round that, but because I'm going to be using this later on, I'm just going to keep it with 4 significant figures. Okay, so that's delta t, which is something that we are supposed to find for problem 94. But now that we have delta t, we can go back to equation 1, or we can go back to what we had here after we solved equation 1 for delta s, and we can find delta s, which is equal to, where is it? Little d. So little d is equal to delta s. Delta s is equal to 80 times delta t, which is 3.568 times cosine of 55 degrees divided by cosine of 10 degrees. So that's just using this equation here. And we get for that 166 feet. You should plug that into your calculator to make sure that it worked out correctly. Okay, so this is delta t, this is d, and now we just have to find, the final speed. So when you're solving a projectile motion problem, my method of attack in general would be to take this equation, draw the vector diagram, look at the horizontal sides, look at the vertical sides. You should have 2 right triangles, so use those 2 right triangles, compare the horizontal side, and then use the same 2 triangles, compare the vertical sides. That should give you 2 equations which are equivalent to those equations that we saw on page 41 of the textbook. So doing that using the vector diagram and looking at the horizontal sides and the vertical sides should give you something equivalent to this equation here and this equation here, because our triangle represents these equations in vector form. Okay, but we have this other equation to use, but you are only going to need this second equation if you are looking for the final speed. I suppose you would also need this equation if you were given information about the final speed and you had to use that to find other things, but I don't know that that's ever the case where you're given the final speed. So if you're looking for the final speed, you need to use this equation here. And do we know the initial velocity? It is 80 feet per second at an angle of 55 degrees. So I'm just going to write that out as 80 times cosine of 55 degrees in the I hat direction plus 80 times sine of 55 degrees in the j hat direction. And you can figure that out from looking at that vector there. And then the acceleration is always pointing straight down. So that's negative 32.2 in the j hat direction, as we saw in a previous problem. I know delta t, so I can take these quantities along with my delta t, plug them in this equation here, and get the final velocity. So using this equation, I have VB is equal to VA, which is 80 times cosine of 55 degrees in the I hat direction, plus 80 times sine of 55 degrees in the j hat direction, minus 32.2 for the acceleration, times delta t, and delta t is 3.568. And the acceleration is in the negative j hat direction. So then do 80 times cosine of 55 degrees, and that will give you the x component of the final velocity. And 80 times cosine of 55 degrees is 45.886. That's in the I hat direction. And then we do 80 times sine of 55 degrees, which is 65.532, minus 32.2 times 3.568, which is 114.890. And 65.532 minus 114.890 gives you negative 49.358. That's in the j hat direction. This is the final velocity, and the units would be feet per second, but they didn't ask us for the final velocity. They asked us for the final speed. So the final step would then be to find the final velocity by squaring the x component, squaring the y component, adding them together, and taking the square root. Because you're squaring the y component, it doesn't matter that it's negative. You can stick the negative sign in the parentheses if you want. It's not going to change anything. And this gives us the final velocity is equal to 67.4 feet per second, where at this point I did round because this is the last thing that we're looking for. And like I said before, if you want to go back and round the time, you can, but I don't care if you leave it with 4 significant figures. And that concludes problem 93 and problem 94.